hear me okay? So I come from Imperial College, but I haven't been there for a while. I have only been at Imperial for 1.5 years. Just as short introduction to what I have done. So I'm actually a chemist, and I have done a BSc in chemistry and a PhD in polymer chemistry in Cyprus, where I come from. And then I did a postdoc in US at Rice University in the bioengineering department, and actually in a group that they were doing tissue engineering with Tony Mikos. And then I moved to UK, where I had a tenure track position at the University of Hull in a chemistry department again. And then I moved to Imperial College when I got a lectureship, and now I'm in a materials department. So even though I'm a chemist, I'm actually in a materials department, because as a polymer chemist, I find many interesting applications in materials. Now, just a short introduction of how you can make polymers. So there are several ways that you can make polymers, and so if you use non-living polymerization techniques like free radical polymerization, that is the easiest you can have, you can make polymers with many different variety of monomers, but the problem is they're not well defined. That means you have very high molecular weight distribution, and you can only make polymers with structures like this one, where the distribution of monomers within the polymer structure is quite random. So if you use living or control polymerization techniques, you have a better control of what kind of structures you can make. So you can control where the blocks will be in the structure, and you also have a much better control in terms of composition, as well as molecular weight distributions, and the 3D structure. So these are the kind of techniques that I use with my group. And I'm an expert in a polymerization method that is called group transfer polymerization, or GTP. So GTP was developed by DuPont in the 1980s, and it's not a method that is used a lot now, but it's the patent just expired, so I'm assuming that this is going to be used a lot more in the future. It is commercially used to make standards, because it produces polymers with very, very narrow polydispersities. The disadvantage is that you can only polymerize acrylates and methacrylates, so you're a little bit limited in terms of the chemistry sometimes. But it does produce polymers with very good control, so well-defined molecular weight distributions, as well as very well controlled in terms of composition and architecture. The other advantage is that you can easily scale it up, so you can actually make kilos of polymers if you want to, while other methods there fail to do so. And it is cost-effective because you use relatively low amounts of solvent, and you do this at room temperature, so you don't have the cost of cooling down or heating up, unless you do it at very big amounts. You have a limitation in terms of molecular weight, so you can only go up to the degree of polymerization of 200. That depends on the monomer, however. So you have a variety of monomers that you can polymerize. So you can have, with red, I put hydrophobic-based monomers, or with hydrophilic monomers. Some of them are pH responsive, and some are also thermo-responsive. So you can make polymers with different functionalities to make smart materials, depending on what you want. So these are hydrophobic, these are hydrophilic, some of them depending on the pH and the temperature. And then you can also make your own monomers that we do at routinely basis to do with monomers with different functionalities if you want to. Now, what we do very well is control the structure. So we can systematically vary the length, so the molecular weight, the degree of polymerization of the polymer. We can keep that the same and systematically vary the composition. So imagine with blue and red, there are two different types of monomers. So you have two different types of blocks here that you can vary the length by keeping the overall length of the polymer the same. You can also have terpolymers, so polymers that contain 3 monomers. You can even go higher than that. This is just an example. And you can vary where the blocks will be within the structure. So if we call A the blue block, and B the green one, and C the red one, we can have A, B, C, and then we can have BAC, and so on. And of course, you can easily make the statistical one, so where the distribution of the monomers is randomly within the polymer structure. But you cannot just vary that. You can also vary the 3D architecture. So you can have linear star-based polymers or higher branch polymers that you can even cross-link further to make gels. That's where you start losing control. So by introducing cross-links, you start losing control of the structure that you're making. But what I'm interested in, what my group is always been studying, is how I can vary the structure to vary the end activity depending on the application that we're looking for. So we systematically vary the structure of the polymers to see how that influences the end properties of the materials or the application. So we do many different projects. What I'm presenting today are polymers that are thermoresponsive. So they have the ability to respond with temperature. So these polymers have a lower critical solution temperature. That means by increasing the temperature, they become more hydrophobic. And if you fine-tune the properties, you can find the temperature where they will make a gel. So in a potential application, you can mix the polymers with cells at room temperature. So this will be a solution that you can syringe. And then if you put it into the body, because the body is at 37 degrees at higher than room temperature, depending, I guess, which country you're in, you can make the formation of a gel. So the polymer now makes a gel, and the cells are actually encapsulated within the gel structure. And so the gels will provide support for the cells to grow and hopefully proliferate. So if you measure the viscosity with temperature at this sol-gel transition, so where you have solution to gel transition, you have you have a transition where you can observe the viscosity going up very dramatically with temperature. And this is where you get the formation of the gel, and this is what we're interested in. And this is the kind of graph we want to have in order to have a very good sol-gel transition for this kind of application. You can visually observe this because at this temperature, the solution is just a liquid, where here it forms a gel, so it doesn't flow down. So you can easily see it by inverting the tube that the polymer solution will just stay on the top because now it's forming a gel. In this study, we've made terpolymers or tri-block polymers, and they were mostly based on 3 different monomers that are shown here. So with green is a PEG-based monomer. PEG is biocompatible, so it's used a lot in bioapplications. Our hydrophobic monomer was N-butyl methacrylate with red, and in blue is the dimethylaminoethyl methacrylate. There is a pH-responsive and also a thermoresponsive polymer monomer. So this is the one that provided the thermoresponsive property for the polymers. And we varied, so we've made tri-blocks. So green is the PEG-based one, red is the hydrophobic, and with blue we have the thermoresponsive and pH-responsive component. And we varied the length of the blocks as well as the overall composition. And we also varied the architecture, so the position of the blocks within the structure of the polymer. And we did a random copolymer to compare that with the block structures. We also did the corresponding ABA blocks, where again we varied the length as well as the composition of the blocks within the polymer structure. So the synthesis is done in a one-pot reaction and is sequential. So in a pot that you have the catalyst, the initiator, and the solvent of the polymerization, you would just add the first monomer, and you have the formation of a homopolymer. With the small star, I'm symbolizing that the active side of the polymerization. So this is where you can still continue to grow the polymer. So if you add another, I have to say that the reaction is 100%, so you have full conversion of the monomer to the polymer, and it's pretty fast, so each step is less than 50 minutes. So with the addition of the second monomer, you have the formation of a diblock copolymer. Again, you still have the active group at the end. And you can add the third monomer to make the a triblock copolymer, as you can see here. All the polymers have relatively low narrow molecular weight distribution, so below 1.19. And during the polymerization, that dispersity increased by increasing the molecular weight. That shows that it's a proper living polymerization technique. We studied the properties, so we did gel permeation chromatography to confirm that the molecular weight increases. So when you go to lower elution volumes, the molecular weight increases, and you have the formation of the first block, the second block, and the third, that is the polymer, and you don't have any traces of the other two precursors to the polymer here. So it was a successful synthesis. And then we studied the polymers in different aqueous environments and studied their micelle formation, so how they self-assembly in water, and also what happens if you change the temperature. That's our main aim, to change tailor the thermoresponsive property of the polymers. So in this study, we varied 2 parameters. Well, I guess more than 2 in a way. So we varied the molecular weight. So the first row is polymers with 5,000 molecular weight. The second one is 10,000, and the third one is 15,000. And by going from the left to the right, we varied the hydrophobic component composition. So 20% weight percentage, 30%, and 40%. And we studied the rheology by increasing the temperature. So what we wanted to obtain is this clear salt-gel transition that you get here. But to our surprise, you didn't get that in all polymers. So obviously, by increasing the polymer molecular weight, you get the formation of gel easier. But if you increase the molecular weight too much, then you have the gel formation at all temperatures. This is not what you want. Similarly, if you increase the weight composition, you again, the hydrophobic component, you again get gels at all temperatures. That this is not what you want. So there is a fine balance, and you have to tailor the composition and the molecular weight to obtain this salt-gel transition that we wanted to get. So we've also varied the structure. So with blue, again, is the thermoresponsive, is a PEG-based monomer. With red is the hydrophobic component, and with green is the thermoresponsive. So you can make micelles that they have these different kind of structures. So this one, even though they all have the same molecular weight, because the hydrophobic component is in the middle, it makes micelles that they are of smaller size compared to the other 2. And that we found out that that's have a significant effect to the end application. So these kind of micelles are the ones that they will self-assemble to make a more stable gel, and those are the ones that we observe a better salt-gel transition. So there was an architecture effect as well as a molecular weight effect on the transition. So ABC is a tri-block where the hydrophobic is in the middle, while here the hydrophobic is at the end bits for the ACB and the BAC structure. And we also compared with the random copolymer that I call here statistical. So overall, the statistical copolymers don't have very good salt-gel transition, and in some cases they don't even make a gel. The ones that always have very good salt-gel transition is the one where the hydrophobic is in the middle. So in different columns, we divide the hydrophobicity. So we use a monomer that is ethyl methacrylate that has a small hydrophobic component, and then the butyl methacrylate that I shown the structure earlier, and then one that has an even higher alkyl side group, so 6 carbons. And we observed that by increasing the hydrophobicity, essentially you get you lower the gel point, so you lower the temperature that you obtain the gel. But the gels that you get with a higher alkyl group, they're not as stable. So the glassy kind of monomers that you used earlier are actually the ones that make a better gel because it's more stable. So the ABC structure, the one with the hydrophobic in the middle, is the best one that has the very clear salt-gel transition. And by increasing the length of the alkyl group, we lower the gel point. And the gel stability is decreased by increasing the length of the side alkyl group. So again, you have to tailor between all the properties that you want depending on the application. In another study, we varied the symmetry. So here you can have a symmetric ABA tri-block where the 2 blocks at the end, 2 A blocks are exactly the same size. And that's the symmetric one, but you can also have asymmetric ones. So in this case, the one at the end has double the size of the first one, and in this case, it has 4 times the size of the first one. And again, we compare with the statistical, and we vary the composition of the thermoresponsive component to 40, 50, and 60. And as we increase the hydrophobic component, the gel point decreases, as we observed before. But we also observed that it's very important to have a symmetric structure. The symmetric structure favors the formation of flower-like micelles, that they then self-assemble to make the gel. So when you don't have the symmetry, you don't get the formation of the micelles as well, and then you don't get as a good gel. So just to summarize the main results, so we varied a lot of different parameters: the molecular weight, the composition, the architecture, and the length of the hydrophobic side group. And the easiest test to do is the visual test, where you invert the tube to see if you get a gel. But we also did rheology. We believe that the optimum molecular weight, at least for the system we're using, is about 7,000. If you go too high, the polymer is not very well soluble, so you ended up precipitating out, and you don't have the formation of gel, but you have a very cloudy solution, and the polymer is just a solid at the bottom of the vial, essentially. The same thing happens with a hydrophobic component. To have some hydrophobic groups there is good, but if you have too much, again, the polymer becomes insoluble in water. To our surprise, the architecture has a significant effect, and we were the first ones to establish this. And if you have the hydrophobic group in the middle, it supports the self-assembly, and it does support the end self-assembly of the gel. So the best one is when you have the hydrophobic component in the middle. And if you increase the length of the side alkyl group, you can lower the gel point. So you lower the temperature that you get the gel, but you also reduce the stability of the gel. So we're currently studying how, by varying the length of the hydrophobic PEG group, you can also affect the thermoresponsive properties. And by increasing the side group, you can, by the PEG side group, you can reduce the gel point, but again, you're reducing stability. We are also studying how the number of blocks can affect the physical chemical properties and of the thermoresponsive properties. With this method, I can make a multi-block, so we can go easily up to 9 or 12. We're investigating how many blocks we can actually make at the moment. And we're also using these kind of gels for 3D printing. So they can be used as surfactants, and they can be used to disperse other materials. So there is a lot of interest in my department in using these polymers to stabilize other materials like graphene to do 3D printing of those kind of materials. So we'd like to thank the 2 students that are currently working on this, and also the committee for inviting me here, and you for being here today. Thank you.